So, moving on from Lewis structures, let's talk about how electrons distribute themselves over entire Lewis structures. So, this brings us back to the concept of electronegativity. So, remember that this is from, there's a chapter in chapter 6, we talked about the Pauling scale of electronegativity, where you can have electronegativities between 0 and 4.0, where 4.0 is the most electronegative atom, and that would be fluorine. So fluorine tends to associate itself with electrons the most of all substances. And then so cesium, so if you look at the periodic table, so fluorine is the most electronegative. And then we go to the other side of the periodic table, cesium and francium have the lowest electronegativity. So there's a chart in chapter 6. So electronegativity is the ability of atoms in a molecule to attract bonding electrons to themselves. So electronegativity tells us to what extent electrons associate with that certain atom. So if you have an electronegative atom bonded to a not so electronegative atom, more of the electrons will associate itself or attract itself to the more electronegative element. So the trend goes from left to right, electronegativity increases, and from bottom to top. So that means fluorine is most electronegative, and then so cesium or francium, but we don't really talk about francium because it's so radioactive. Uh, Cesium is the least electronegative. So when we have two atoms bonded to one another, sometimes there's a difference in electronegativity. So there's an imbalance in electron density when you look at that certain bond or molecule. So if you take the difference in electronegativity of the two atoms involved in that bond, that can tell you the degree that electron density is distributed. So if there's a large difference in the delta En, so the difference of electronegativity of the two atoms, if there's a large difference, we call this an ionic bond or a ionic bonding description. So if you take fluorine or any of the nonmetals have pretty high electronegativities, while the metals on the side of the periodic table have low electronegativities. So if you take the difference between a big number and a small number, the difference is going to be pretty big. So that tells us a large difference in electronegativity means ionic bonding. Also, we know that if we combine a nonmetal and a metal, we get an ionic compound. So that makes sense that this agrees with a lot of what we've talked about thus far in the semester. Right? And so let's say you make a molecule with two of the same element, so like a chlorine and a chlorine. All right, so if you take the difference in electronegativity of two chlorines, the difference is going to be 0 because the value for electronegativity of chlorine is the same. So if you take the same number and subtract it from itself, you get 0. So a small or no difference in electronegativity is a covalent bonding description. All right? When there's a small difference in electronegativity. So then if there is a medium, moderately large uh, difference in electronegativity, this is what we call a polar covalent bonding description. So ionic compounds typically have ionic bonding. Covalent compounds typically have covalent bonding. There exists a intermediate between the two, and that's what the moderate difference is. Polar covalent bonding. It's essentially it's just the intermediate between ionic and covalent. We don't necessarily have a purely ionic bonding description and a purely like not everything can fit in those perfect ionic or perfect covalent bonding descriptions. It's kind of this continuum. So that's where this slide is. The nature of bonding is a continuum. So depending on what two atoms are involved, that bonding description can lie anywhere along this trend, where this is our delta En increases going this way, increases. So this is a delta En or difference of electronegativity of 0, and then we increase to about 2. So depending on the difference between electronegativities of the two atoms, it can lie anywhere along along this continuum. So the ionic and the covalent bonding are the two extreme cases where if we have a difference of electronegativity of 0, that's a purely covalent compound. That would be like two chlorine atoms equally sharing electrons to fulfill their octet. So like an example of a purely covalent compound would be like hydrogen or chlorine. So since the atoms are the exact same, there's no one preference for an electron to associate with whatever atom because both of those electronegativities are the same. Then on the flip side of things, if there is a large difference between electronegativity, then an electron transfer is more likely to happen because one of the atoms has a very high electronegativity. So I'll just make up something like cesium chloride or something. So cesium chloride has a low cesium has a low electronegativity. Chloride has a high electronegativity. So this ionic compound would typically exist as an ionic compound where there's a complete electron transfer. This contrasts itself to a purely covalent compound where, since the electronegativities are the same, or the difference, the delta is 0, there's an equal sharing of electrons. So I could always write this out as, this is hydrogen, where there's an equal sharing. Versus this cesium chloride, the chlorine has an extra electron associated with it. So between these two extremes, the range of electronegativity difference that we see in a polar covalent compound can range anywhere from the high end is like 1.9, between 1.9 and 0.4 delta En will be considered a polar covalent compound. So just to, I guess, summarize it. So do I talk about that in the next slide? No. So ionic, its electronegativity difference needs to be greater than 2 or 1.9. Polar covalent, is anywhere between 0.4 and 1.9. And then finally, pure covalent is anything less than 0.4. So that's our rule of thumb. Okay, so let's look at some example compounds. So here I have 3 different substances. So a compound first containing cesium and chloride, another one containing H and Cl, and another Cl and Cl. So this says predict bonding descriptions for each of the following compounds. So our first step in order to predict the bonding description, essentially we're going to answer, is it ionic? Is it polar covalent? Or is it a pure covalent compound? So that's the question we're being asked. So so step 1 would be to look up the electronegativities for each of the atom to get the delta En. Because once we have the delta En, then, or the difference of electronegativities, then we can use this chart to determine what category it lies in. So the electronegativity I will, if ever I ask a question like this of you, I will give you a chart with electronegativities of all the elements. You just have to know how to use it. So the electronegativity of cesium is 0.8. The electronegativity of chlorine is 3.0. So the delta electronegativity of the compound of cesium chloride is 2.2. I'll rewrite this. So delta En equals 2.2. All right. So this means since 2.2 is larger than 2, we're going to say that this is an ionic bond. Or more specifically, we can say electron transfer occurs where the electron will go to the more electronegative atom. So electrons are more attracted to chloride than cesium. So that's why we will see something, since the electron transfer occurs. So electron transfer occurs, so we will have a cesium cation and a chloride anion. Cation, anion. So I'll note that with this electron transfer, it's a complete electron transfer occurs. All right, so let's look at, let's go on the other side. So let's look at chlorine and chlorine now. So again, we're asking ourselves, what's the difference of an electronegativity of chlorine and chlorine? So if you look up the electronegativity of chlorine, it is 3. So the change or the difference in electronegativity of a chlorine and a chlorine will be 3.0 minus 3.0, so it is 0. So this 0 is less than, 0.4. So this is a pure covalent bond. So what does that mean? It means that there is equal sharing of electrons between both chlorine nuclei. All right. So since it's equal sharing, its structure will look like our Lewis dot structure. So it will be Cl. They're sharing those 2 electrons, right? So oftentimes people will draw the actual bond between them. So this is what diatomic chlorine looks like, where there's an equal sharing of electrons. All right, and finally, so those are the 2 extreme cases. We have pure covalent and then ionic bonding, where there's a complete electron transfer versus just equal sharing. Now, the last bit here is between hydrogen and chlorine. So again, let's look up those electronegativities. So the electronegativity of hydrogen is 2.1, and then the electronegativity of chlorine again is 3.0. So the delta En for this is equal to 0.9. All right. So this value is between 0.4 and 1.9. So this would be considered a polar covalent compound or bond. I think that's what we're talking about, the bonding description. Okay. So to describe what this looks like, we can say that both, so it's going to be, the description is going to be between that of ionic and covalent. So we can say that both nuclei attract the shared electron pair, but not equally. So an equally shared electron pair would be like our chlorine example. So electron pair shared equally. But in HCl, the electron pair is not shared equally. So both attract shared but not equally. We can say that it's not equally, not, how should I say this? So we can just say it's shared unequally, but not enough to make a complete electron transfer like in an ionic case. So we can say that this is an incomplete electron transfer. I don't even want to say that. It's just the electron density is shared unequally along the 2 atoms, but it's not a complete electron transfer. So maybe that's what I want to say. A not complete electron transfer. So what will this look like? So this is unequal sharing. So it will look more like this. So we have an H and we have a Cl. It is still considered covalent, so we're going to draw a bond here. But because chlorine is more electronegative, more of the negative charge will reside on the chlorine side, while it'll be more positive on the hydrogen side. So I have these little lowercase deltas to signify partial charge. So I will show you what this means in the next slide. But yeah, this delta just means that there is a little bit more negative electron density on chlorine, and it's a little bit more positive on um, hydrogen. So this is a different. It just shows bond polarity, but it's not a complete electron transfer like we have in these ions. So it's not a complete ion essentially. We're just signifying there's more electron density on this side. All right, so that is that chart. So I've been saying electron density a lot, so let's actually define what that is. So here's a picture of a heat map of electron densities of different substances. So we have a purely covalent diatomic fluorine on this side, while we have a completely ionic compound like lithium fluoride on the other side. And then obviously this is our polar covalent substance. So you can clearly see the differences uh, between these three substances. So the red means more electron density. So again, I keep saying electron density. What does that mean? So the red just means that electrons are spending more time on the fluorine side than the lithium side. And that really has to do with the large electronegativity of fluorine. And, it's closer to 4 than for lithium. But then if you see on our in our fluorine example where it's purely covalent, it's just the same color all around because all electrons are shared equally. Both fluorines have the same electronegativity, so there's no driving force for electrons to go on either side. It can spend time on any part of the fluorine equally. And then you can kind of see the hybrid color gradient of HF. So HF is our polar covalent substance where the bonds have the shared electron pair, but the sharing is unequal. So you see that the electrons spend more time on this fluorine side and less time on the hydrogen side. So the blue means less electron density. All right. And so this has to do with fluorine having the larger electronegativity than its counter cation or hydrogen and lithium. So that's why the fluorine side of the atom is red because the electrons spend more time on the fluorine side. All right, so that illustrates electron density. There's also another way that we can show bond polarity or how electrons distribute over bonds. Um, so bond polarity leads to, so the difference of electrons spending time on either side of the bond brings us to what's called a bond dipole. So if you've taken physics, you might have talked about dipoles a bit. So just like magnets, when you talk about dipoles, charge separated ions also exhibit dipoles. So I'm going to define here dipole moment, or mu, is produced by two equal but opposite charges separated by r, a given distance. And so the equation for dipole moment, mu, is equal to q, so the charge separation, or sorry, the charge that's being separated, times r, or r is the distance that it's separated by. All right, so you can kind of think of these two red and blue balls as a anion because it's Q minus, so it's a negatively charged species, while Q plus is the cation because it's positively charged. So you can just think if we have a cation and anion that's separated, there's a dipole moment between those two things. That charge separation and the distance between those two atoms create this dipole moment. And that leads us to bond polarity. So here are some examples of compounds that exhibit dipole moments. Larger dipole moments, you can get a larger dipole moment by either increasing the charge or increasing r, the distance between those two charges. So you can see here that so Q will be also related to the difference in electronegativity. So if the difference is large or the radius is large, then you'll get a big dipole moment if the charge separation is larger. So HF has a pretty short bond length, but a pretty large electronegativity. So its dipole moment is going to be pretty large. All right. So this is compare this to HI. Iodine has a pretty small electronegativity, so its actual electronegativity difference is pretty small. All right, and so its dipole moment is also pretty small. All right, and then HCl and HBr are kind of between those. You can see here that the trend that the change in electronegativity decreases. And then I think overall our dipole moment, um, or dipole moment, it's just in a different unit, also decreases. All right, okay, let's keep going. Oh, I think this is the last slide. All right, so indicating bond dipole. So bringing back to the electron density distribution that I showed in the previous slide, red just means more electron density, and blue means less electron density, and then green just means in the middle. All right, so there are two different ways we can indicate bond dipoles, or just indicating that one side has more electronegativity or has more electron density than the other. So bond dipole just means, remember, unequal distribution of electrons. All right, so the one way we can show unequal distribution of electrons is through partial charges. So this is the delta plus and delta minus. So it just means that so delta just means partial. So there is a partial positive charge on one end of the molecule and a partial or delta minus would be a partial negative charge on the other side. So, oh, this is backwards. Whoops. So this should be delta plus. Oh, wait, no, that's right. No, that's right. Whoops. Okay, scratch that. So a delta plus means that there is less electron density, or that it's more positive on one end. And then a delta minus would be more electron density, more negative on the other end. So if we wanted to do partial charges on HF here, all right, so fluorine has more electronegativity than hydrogen. So I'm going to say that on the fluorine side that we have a partial negative side on the fluorine side and a partial positive on the hydrogen side. All right, and then finally, and then obviously if you had a purely covalent compound, you would never have to use partial charges because everything's distributed evenly. No one side of the molecule has more electron density than the other. All right, and so all of these molecules actually up here have a partial positive on one side and a partial negative on the other side. All right, and then finally the other way to indicate bond dipoles is a dipole arrow. So the arrow indicates the magnitude and direction of the shift of electrons. So the arrow will always point towards the more electronegative atom. So the arrow looks like this. So I always like to remember the side with the cross, it looks like a plus. So this is the more electropositive side of the atom, and then the arrow points to the more negative side of the molecule. So if I wanted to do that for all of these molecules up here, all of the arrows would be pointing this way. But remember, the arrow also indicates the magnitude of the shift of electron density. So HF has the largest, delta En is the largest for between hydrogen and fluorine, and then the delta En for iodine is the smallest. You can actually just see all those up here, right? The electronegativity differences. So it decreases going this way. So that means since the delta electronegativity decreases from going from fluorine to iodine, that means that the dipole arrow has to get smaller because this arrow will reflect so the length of arrow reflects the delta En between the two atoms that's creating the bond dipole. So if I were to actually draw it, does that look smaller? Not really. Yikes. Okay, try to make them smaller. I'll just make them comically small. So something like that. So all the arrows are pointing the same way because it's pointing to the more electronegative atom, which is the halide in this case. But because the electronegativity difference for HF is a lot larger than the electronegativity of HI will have the, smaller the smaller dipole arrow. And so here's just some examples, but I kind of went more in depth with these 4 examples up here. All right, so that concludes part 2 of, or sorry, no, this is part 1 of chapter 7. So stick around. We will go over part 2 of chapter 7, and that is going to go over. So we have gone through all of these chapters. Now this last part, it has a lot of slides to it, but I think we'll go through it pretty quick, is molecular structure and polarity. So we're going to look at the molecular shape and put a lot of practice into drawing Lewis structures. All right, stick around.